Hey everyone, this is a video lesson that I'm using in my AP Calculus AB class, and I'm putting it online in case it would be helpful to others as well. In this section, we are going to talk about a rule that students often in beginning calculus struggle with, and it is called the chain rule. Now, I should mention before we begin that there is a printable set of guided notes that you can use to follow along with the examples that I'm going to do in this video. The first thing that you see in that set of notes is a little warm-up. And usually when we're in person, I love watching my students do this, and you might think I'm evil for saying this, but it's because it starts out really easy, and it's so funny because I watch them get confident when they do it. They're like, oh yeah, I know this, right? The derivative of sine of x is cosine of x. Easy peasy. And then they move on and they go, oh yeah, the derivative of 3 sine of x is 3 cosine of x. No big deal. And their confidence is built up so much just by those two that they're ready to tackle number 3. For number 3, we need to use the product rule, right? Now we don't just have a constant multiple of 3 in front of our sign like we did with number 2. We have a 3x. And so therefore, we should use 1d2 plus 2d1, as I like to say, or first times derivative of second plus second times derivative of first. The derivative of first is 3. I am going to put that in front, though, like that. And then my students get to number 4, and they go, what? What is that? What is that? And it looks different. And some of them, tackle it, they try it, and others, not so much. And then what I say to them is, okay, yeah, this looks different, right? Here we have sine of x, here we have sine of x, here we have sine of x. All of a sudden, number 4, we have sine of 3x. What do you do with that? And I usually tell my students to just try something. Like, what do you think the answer is? And the most common response I get, which I'm going to tell you, it's wrong, is cosine of 3x. I shouldn't say it's wrong. It's just not complete, okay? So what I then typically do is I have my students, so please keep in mind, this is not done. Not done. It's not really wrong, but not done, okay? What I typically have my students do is watch a cool little YouTube video that I found. Yes, I'm telling you to go to a different YouTube video in this YouTube video. No, not really. But I've always used this little chain rule intro video where the teacher uses this example and says, well, it's definitely not cosine of 3x. And all the students go, oh. And then throughout the video, I have them answer these questions. Now, if you're one of my students, I have directed you to that video, and so you probably can skip this part of my video. But for those of you who haven't seen that one, I will go over this with you now. Why is the derivative of sine of 3x different than other derivatives we have done? Well, it's because sine of 3x is called a composition of functions. Okay, let's write that, and then we'll talk more about what that means. It is a composition of functions. So it's really kind of key here that you understand what I mean by the word composition before we talk about what the chain rule is. Okay, so what is a composition of functions? Well, I like to think of it as just a function within a function. That's not really a great definition. It's pretty loose. Really, any function could be considered a composition of functions by that definition. Okay, but more specifically, a composition of functions is when you have two functions. I'm just going to make two up, like f of x is equal to the square root of x, and g of x is equal to x cubed minus 8. Okay. A composition of functions is when you replace the x in one function with another function. So prior to calculus, a lot of students may have learned this in other classes as fog or goth. Does that sort of sound familiar? Sometimes we use this notation for compositions of functions. I'm going to tell you right now, I don't love that. I just never have. I like this better. I think it just is more intuitive and makes more sense for what we need to do. Okay. And so these two things mean, with these functions, specific functions, mean different things. Okay, so f of g of x says, take your f of x function and replace the x with g of x. And so that would look like this. I would have the square root of x cubed minus 8. G of f of x says, take the g of x function and replace the x with the square root of x. So that would look like this. The square root of x cubed minus 8, which could be simplified a little bit to what? X to the 3 halves power minus 8. Okay, so the composition of functions, again, is when you replace all of the x's in a function with another function. And whenever you have a composition of functions like this, you need to use the chain rule to differentiate. So that answers number 2. When do we use the chain rule? When we have a composition. Or you could think of it as when you don't just have a plain x inside of a function. So, when I give my students something like y equals sine of x, just sine of x, a plain x in the sine function, they're easily able to differentiate that, just using the rule that the derivative of sine is cosine. However, when I give them sine of something that is not just a plain x, if it's anything else in here besides just a plain x, like a 3x, it could be a square root of x. It could be an x squared plus 3x minus 9. I don't know, whatever. If it's not just a plain x, that is when we need to use the chain rule. Okay, so number 3, briefly describe how to use the chain rule. Okay, I'm going to describe it verbally, and you can write down whatever you want here, just because my handwriting is horrible on these, and I need to give myself a break. Okay, so here's how we use the chain rule. You differentiate the outer function first while bringing the inner function along, and then you multiply by the derivative of the inner function. Okay, I'll say that again in maybe another way. When you use the chain rule, you differentiate, I don't know if I'm going to say it in a different way, you differentiate the outside function, carrying along the inside function, and then you multiply by the derivative of the inside function. Did I say it any differently? I don't know. Okay, take what you can from that. We're going to write an actual formula a little bit later in the notes. Okay, let's just move on now to number 4. What is the derivative of sine of 3x? Okay, it is this. Watch here, I'm going to say it again. You take the derivative of the outer function. The outer function here is sine, so the derivative of sine is cosine, while bringing the inner function along. So listen to this. The derivative of sine of 3 of x is cosine of 3x. Did I say 3 of x up here? I don't even know. I'll say that again. The derivative of sine of 3x is cosine of 3x. However, you then need to multiply by the derivative of the inner function. And so the derivative of 3x is 3. That is our derivative that we need up here. Remember when I said this was not done? Now it is. The derivative of sine of 3x is, probably lost my pen width, thickness, whatever. Cosine of 3x times 3. And the chain rule is often used for trig functions because it's, many cases that we might not just have a plain x inside of a trig function, and so we will need to use chain rule for those instances. Okay, I think the next thing I have in this set of notes is a little bit of a U-try section where you can try to apply the chain rule with various trig functions. So again, keep in mind that when you use the chain rule, you are differentiating the outside function while carrying the inside function along, and then you're multiplying by the derivative of the inside function. I'm going to pause my video and put answers to these in here. I suggest you pause at this time and you try these, and then I'll come back and explain. Okay, and I'm back, except as I was writing these down, I decided maybe I should go over part D as an entire group instead of just writing it down, because a lot of students get confused with this one. But before we go over that, let's check our answers to A, B, and C. And I did not rearrange any of my pieces here, just to very clearly show the chain rule. Typically this 5, we could put it in front with this negative and make this answer -5 sine of 5x. But we're just getting started with the basics of chain rule, so I am going to leave it in this form. Okay, so in A, I had the function y equals cosine of 5x. I took the derivative of cosine of 5x, which is negative sine of 5x, but then I multiplied by the derivative of 5x, which is where this times 5 is coming from. Similarly, in B, I had the function sine of x squared. I took the derivative of sine of x squared, which is cosine of x squared, but then I multiply by the derivative of x squared, which is 2x, to complete the derivative. In part C, the derivative of tangent is secant squared. Therefore, the derivative of tangent of 2x plus 1 is secant squared of 2x plus 1 times 2, because the derivative of 2x plus 1 is 2. Okay, finally, in part D, we have cosecant of x cubed, and the formula for the derivative of cosecant is negative cosecant cotangent, right? Like if we have cosecant x, then the derivative is negative cosecant x cotangent x, right? Okay, so since there are two functions in the derivative, when you do your derivative rule, the inside of your original function needs to go into both of those functions. So you're going to be writing x cubed twice. Okay, it's going to look like this. The derivative of the outer function, cosecant, is negative cosecant of x cubed cotangent of x cubed. And then we multiply by the derivative of x cubed, which is 3x squared. You only do it once, though. Okay, so those are some simple examples of how we apply the chain rule with some trig functions. And now what we need to do is write an actual, formal rule for the chain rule. Okay, now I have two different things here. I have two different ways that we can express it. The top one that you see in blue is how the textbook that I use expresses it, but to be honest, I don't love it. I've already told you I don't like that notation a whole bunch. So I'm just not a fan of this. Okay, so notice this big or here, and I like this one a lot better. I think it's easier to see exactly what you're supposed to do, and so if you are taking notes for yourself, I would recommend that you write down this one. And here's what it says. It says if you have a composition of f being the outer function, g of x being the inner function, you first take the derivative of f. Notice that that's denoted with f prime, bringing g of x in that derivative function, and then you multiply by the derivative of g of x, and that's shown out here with g prime. Sorry for the scribbles. Now, for a whole bunch of other examples, we are just going to use the chain rule. Oh, except first I want to show you this. I found this online somewhere. I can't remember where. I think it's cute, but it's also a little scary. Okay, so you can think of a composition of functions as a pregnant mother. Like if it's f of g of x is the baby, f of x is the mother. So again, this is like f is the mother, g of x is the baby. And it says you differentiate the mother, leave the baby inside, and then you differentiate the baby. I don't know, differentiate the baby just sounds like a little bit evil, but there you go. Okay, now let's do a whole bunch of examples where we're just going to use the chain rule. Take a look at example 1. An object moves along the x-axis so that its position at any time t greater than or equal to 0 is given by this function x of t equals cosine of t squared plus 1. We are to find the velocity of the object as a function of t. Okay, well, if this is our position function, when we take a first derivative of that, we get velocity, right? X prime of t is the same as v of t. So let's differentiate this mother and baby and we will get our answer. The chain rule says we take the derivative of the outer function first. The derivative of cosine is negative sine. The derivative of cosine of t squared plus 1 is negative sine of t squared plus 1. We then multiply by the derivative of t squared plus 1, which is 2t. You might want to rearrange the factors here, and write this as negative 2t sine of t squared plus 1, just to make it look a little bit cleaner, but you don't have to. Take a look at example 2. Very similar. Differentiate sine of x squared plus x with respect to x. Okay, so I don't really have an equation here, so I'm just going to go for it. Let's just write the derivative. The derivative of sine is cosine, so the derivative of sine of x squared plus x is cosine of x squared plus x. You see how that always matches? And I say it on purpose like that so that we catch it. The derivative of sine is cosine. So the derivative of sine of x squared plus x is cosine of x squared plus x times the derivative of x squared plus x, which is 2x plus 1. This is another one where maybe I would suggest that you rearrange, just because sometimes, a student might be inclined to say, well, should we multiply these together? No. Let's put the 2x plus 1 in front of the cosine, and the x squared plus x is in the cosine. Yay. All right, take a look at this next one. If y equals the quantity 3x to the fourth minus 5x cubed plus x squared minus 2x plus 9 squared, find y prime. Okay, so this is like a twist on a really simple rule. It's like the first rule that students learn, at least in my class. Maybe I shouldn't use an arrow. Do a different color and do a little note out here. I want to show you something. Note. We know that if y equals x squared, then y prime is 2x, right? Well, watch this. I'm going to express this a little bit differently. I'm now going to write y equals u squared. And often in calculus, we use the letter u to denote a function of x, okay, or to denote a function. It's not just a plain variable. It's showing a function. So u is a function of x, okay? Then y prime is equal to 2u, just like x squared becomes 2x. But you then multiply by the derivative of u with respect to x. Coming up very shortly, you are going to see this a whole lot when we talk about a lot of other different derivative formulas. You see that times du dx in the formulas, and it's just there to remind you of that part of chain rule. Okay, so in part B, we're going to apply it like this. Let me go back to my blue. To find y prime, we are going to do the derivative of the outer function. The outer function is just the squared, and we know that just becomes 2, a coefficient of 2 and a power of 1. So it looks like this. A coefficient of 2 in front of all this stuff. This is the u, by the way. That stuff is the u. With a power of 1. You don't really need to put that there. This is the 2u. And then we need to multiply by the derivative of the u. I totally forgot what I was doing for a minute. Just check my answer key. Yeah, that's right. That's good. And there's our answer. Woohoo. No rearranging needed with this one. Okay, now this section, just going to warn you, real fast gets really crazy. Okay, students start to go, what is going on? There's so much. Chain rule's tricky, and then like when you throw in some of this other stuff, but we're going to do it. Take a look at example 3. Find the derivative of g of t, and g of t is equal to tangent of 5 minus sine of 2t. Now, this example is so crazy that it needs its own name. It's called a 3-link chain. It's called a 3-link chain because we're actually going to have to apply chain rule a couple of times. And here's why. I'm going to put parentheses here. I'm going to insert some parentheses where they could go. They're dropped just for whatever reason, but they don't need to be, and it's right there. Okay, so let's talk about a plan here. To get g prime, you know what? We're just going to go with the big bold. Yep, we're just going to go with it. To get g prime, we need to take the derivative of the outer function, bring the inner function along. Okay, let's start there. The derivative of the outer function is secant squared. Bring the inner function along. And then we multiply by the derivative of the inner function. But the derivative of the inner function is going to also need chain rule. Watch this. The derivative of the inner function, that's what I'm working on right here. Derivative of 5 is 0. Phew, an easy part. The derivative of negative sine of 2t is negative cosine of 2t, right? The derivative of sine is cosine. So the derivative of negative sine is negative cosine. The derivative of negative sine of 2t is negative cosine of 2t. However, there's a 2t in there. There's not just a plain t. So you also need to multiply by 2. So this is called a 3-link chain because we differentiated technically 3 times. We differentiated the tangent. We differentiated what was in the tangent. But what was in the tangent was a sine, and so we also had to differentiate what was in the sine. I'm not going to simplify that, though. That was enough. I hope you understood it. Next. Example 4a. Find the derivative of y equals the square root of 2x. Part B, how is this different than the derivative of y equals 2 times the square root of x? Okay, well, I'm actually going to answer part B first. How is differentiating this, which is new to this section, than this, which you should have been able to do before this section? Well, chain rule. That's the difference. This one needs chain rule. This one does not. Okay, so to answer part B, y equals 2 root x. Let's start with the simpler one. Does not use chain rule. Right? Because we could rewrite it as 2x to the 1/2 power. And then to get y prime, we would just do power rule. 1/2 comes down in front, multiplies with the 2, making the coefficient 1. Subtract 1 from the power to get your new power. So we have x to the negative 1/2 is the derivative there. This one, though, the square root of 2x, does need chain rule, or does use chain rule. So maybe I shouldn't do y prime yet. Here's why. Lost the word rule. When we rewrite this square root as a power, we need parentheses around the 2x to group them together and the 1/2 power on the outside. So what we have here is an outer function of a 1/2 power and an inner function of 2x. So now to get y prime, apply the chain rule. The derivative of the outer function is first, bringing the inner function along. So you will still have your 2x in here. The 1/2 goes in front as a coefficient. Subtract 1 to get your new power. So negative 1/2 power. Then multiply by the derivative of 2x, which is 2. The outside factors here can multiply together to get 1. And so we could simplify this to 2x to the negative 1/2 power. That's our answer to part A, by the way, right? Yay. Does that make sense? I hope that makes sense. So with chain rule, by the way, we call it chain rule because it's like there's links to the derivative together. Notice that there's always this thing where you have one part of your derivative, then times another part of your derivative. I hope you've noticed that. And, you know, that's a characteristic, a key characteristic that you'll need to take with you when you do chain rule for yourself. All right, I warned you, these examples get really crazy really fast. Here we go. Find y double prime if y equals cotangent of 4x. Okay, woo! All right, just a quick reminder. If you have cotangent of x, then your derivative formula is negative cosecant squared x, right? Here we have cotangent of 4x, so the derivative is negative cosecant squared of 4x times 4, because this is not just a plain cotangent of x, it's a cotangent of 4x. Now that's just the first derivative. We need to get a second derivative here. However, I think we should rewrite this in a little bit of an easier to understand fashion before we get that second derivative, okay? First of all, to differentiate a trig function that is raised to a power, I'm just going to tell you that this notation, the way it's written here, is not helpful at all. Some people can figure it out and do it, but most students benefit from seeing it like this. Cosecant squared of 4x means cosecant of 4x quantity squared, right? Cosecant squared means the cosecant function is squared. Now, let's not lose our factors out here. We have a negative and a 4, so I'm going to put that right here as a negative 4. Okay, so I did not do a second derivative yet. I just rewrote the first derivative, and what I did was I pushed that power of 2 on the outside of a set of parentheses around the cosecant of 4x. Does that make sense? I hope so. Now let's do a second derivative, and this second derivative is another example of a 3-link chain, right? We have an outer function being the squared. We have inside of that a cosecant, but inside of the cosecant of 4x. Okay, let's do it. Take the derivative of the outer function first, bringing the inner function along. Remember, bringing the inner function along means this stuff's going to come down as you do this derivative. The 2 comes down and multiplies with the negative 4, making a negative 8, and there's a power of 1 here now. That's the first link. Second link, multiply by the derivative of cosecant of 4x. That is negative cosecant of 4x cotangent of 4x. This is like one where I'm like, let me check my key. Times, third link now, we're almost done. Do you know what it is? 4. The derivative of 4x is 4. Throwing some of that stuff together, you could simplify to 32, because negative 8 times negative 1 times 4 is 32. Cosecant squared of 4x cotangent of 4x. And we did it. I did it. Did you do it? Did you get it? There it is. I'll tell you what, when I was about to, I pulled up these set of notes to, start to record or think about recording, I was like, woohoo, this is going to be fun. I don't even know how long this video is. I don't want to know. Keep on going. Let's keep on going. Example 6. Find the slope of the line tangent to the curve y equals sine of x to the 5th power at the point where x equals pi over 3. Okay. So in this example, you don't see the word derivative anywhere. You don't see find y prime or find dy over dx. Okay, but we know that's what we need to do, right? Because of this word. If we are finding the slope of a tangent line, okay, these words I should say, finding the slope of a line tangent to a curve at a point, then we need to do a derivative. So that's the first priority here. Let's get y prime. Or, you know what? Why don't we change it up for this one and call it dy dx using chain rule. The outer function this time is not the trig, it is the power. The 5 comes down in front of the sine of x and is now to the 4th power. Derivative of the outer function, bringing the inner function along. Multiply then by the derivative of the inner function. Okay, that wasn't so bad compared to the last one, right? Now we just need to sub in pi over 3. So that looks like this. And if you don't love this notation, you could change it to just m for slope of your tangent line. Okay, and now we just need to evaluate. Okay, let's see. Pi over 3. What is pi over 3? That's 60 degrees, right? I seriously have to think about this so hard. If I'm like, don't look at your answer key, do it. Okay, sine of pi over 3. What is that? That's sine of 60. Okay, so on our unit circle, that's going to be square root of 3 over 2. Right? I was thinking about how sine is the y-coordinate on the unit circle, and it goes up root 1 over 2, root 2 over 2, root 3 over 2 as you're moving along for your y-coordinate. So it is root 3 over 2 to the 4th power times 5. Cosine of pi over 3 then is a half. Because cosine is the x-coordinate, so it goes root 3 over 2, root 2 over 2, root 1 over 2. Yeah, I just looked at my key. It's like, yeah, right. All right, now going from there, are any of you screaming, just use your calculator? Just use the calculator. No. Okay, the square root of 3 to the 4th power is 9. 2 to the 4th power is 16. Finally, multiplying that all together, we get 45 over 32. Yay, we did it. Finally, one more example. We're almost at the end. One more example that uses slope. Okay, example 7 shows that the slope of every line tangent to the curve, y equals 1 over 1 minus 2x to the 3rd power is positive. All right, so we're going to do it. We know that we need to do a derivative, at least for sure, right? Because we see the word slope of a tangent line, and we definitely know that we need to use chain rule because that's the lesson we're in. All right, first of all, let's talk about how to do that, and then we'll worry about this showing that it's positive stuff. Okay, that might just fall into place. Don't worry about too much of it at the get-go. Just think about, what do I need to do as my first step? Derivative. Okay, but actually, before we do a derivative for this one, I'm going to tell you something that'll be helpful. You should turn this quotient into something with a power. That way you can easily just apply chain rule instead of quotient rule with chain rule. Here's what I mean. There's just a 1 in this numerator. So we could write y as one quantity, 1 minus 2x, raised to the negative 3 power. Right? Does that make sense? Take it out of the fraction, make the power negative. And now to do your derivative, you're just using chain rule like we have with the others. Okay, so dy over dx is -3 times 1 minus 2x. Be careful, subtract 1 from -3, and that gives you -4 as your power. Times, here's the chain, second part of the chain, the derivative of 1 minus 2x, which is -2. Now let's put that back into a rational form. -3 times 2 is 6. That will be your numerator. These numbers do not have a negative power with them, so they do not get moved to the denominator. You can multiply them together. But the 1 minus 2x will go to the denominator with a +4 power. Now, we're trying to show that the slope of every line to this curve is positive. Well, that means that our derivative has to be positive everywhere. Okay, so watch this. This is how I do it. I'm sure there's a fancier way, but I'm tired, so here's what we're going to do. When you have a number divided by another number, you could have a positive from a positive divided by positive or a negative divided by negative, right? Okay, well, we have a positive here. Positive 6, right? 6 is greater than 0, positive. And what do we have here? Hopefully a positive, because if you have a positive in the numerator, you have to have a positive in the denominator for everything to always be positive, which is, again, what we are trying to show. Is that the case? Is this always positive? Yes. Why? Why is it always positive? Because it's a quantity raised to an even power, right? 1 minus 2x does not necessarily have to always be positive, but when you raise it to the 4th power, yes, it does. It has to be positive. So there we go. We showed it. Okay, everybody. As usual, I hope this video lesson was helpful. Bye.